Hello everyone, welcome to Recitation 8. This week's topic was improper integrals, and I will solve questions on this subject. If we do some review before starting solving the question, an integral is improper if it's one of these types. First type was either a or b is infinite, or both. And second type was there exists c on a and b, interval a and b, such that f is unbounded at that point. And the third type is either a or b infinite and f is unbounded at c. Now, if an improper integral a to b fx dx has an finite value, then it's said to be convergent. Otherwise, it is divergent. If we try to find the value of this integral, we can look at the limit. Let's say this integral is improper at b. So we can look at the limit r goes to b from left side, a to r fx dx. And if this limit exists, we can say that this integral is equal to value of this limit. Otherwise, we can say that this integral is divergent. Now, if we pass to our first question, which is evaluate the improper integrals or show its divergence. Now, our first integral is 1 to infinity dx over 3x plus 1 square. Now, our b is infinity right now. And 1 over 3x plus 1 square is bounded and continues on 1 to close to interval 1 to infinity. So, type of this improper integral is 1. Now, if we try to find value of this limit. Now, RB is infinity, so we need to look at that limit big R goes to infinity 1 to arch 1 over 3x plus 1 square dx. We need to find value of this integral. Now, we need to solve this integral, and solution of this integral 1 over 3x plus 1 square dx is equal to 1 over 3 minus 1 over 3x plus 1 plus c. And this is exercise for you. You can show that this integral is equal to this one. Now, if we come to our limit, this one is equal to limit r goes to infinity minus 1 over 3 times 1 over 3x plus 1. This is between r to 1. So this limit is equal to limit r goes to infinity minus 1 over 3 1 over 3x 3r plus 1 plus 1 over 3 1 over 3x plus 1 3x 1 3 times 1 plus 1. So this limit is equal to limit r goes to infinity minus 1 over 3 times 3r plus 1 plus 1 over 3 times 1 over 4. Now, we know now this one is a number. This goes to 1 over 12, and this one goes to 1 over infinity goes to 0. So limit is equal to 1 over 12. So our integral 1 to infinity dx over 3x plus 1 square converges to 1 over 12. So, this is the solution of part A. For part B, at the part B, we have the question draw the line between two pages. Minus pi to infinity sine 4x dx. As you know, sine x is bounded everywhere. So sine 4x is bounded and continuous on minus pi to infinity. And b is equal to infinity. So it is type 1 again, like the first part. Now we need to solve this limit again. Again we need to find this limit. Limit r goes to infinity minus pi to r sine 4x dx. Again, what is the integral? Sine 4x dx is equal to, integral sine 4x dx is equal to 1 over 4 minus cosine 4x plus c. Now, so this limit is equal to limit r goes to infinity. Value of this integral is 1 over 4 minus cos 4x is between minus pi and r. Now we can write this limit as limit r goes to infinity 1 over 4 minus cosine 4r plus cosine 4 pi. Now, this one goes to 1, but this one is not exist. So we know that this limit does not exist. We have cosine 4r, and this limit goes to 1 and minus 1 continuously. So limit does not exist. So this implies that minus pi to infinity sine 4x dx is divergent. Our third question is integral 0 to pi over 2 secant x dx. We know that when x goes to pi over 2, secant x goes to infinity. So secant x is unbounded when x approaches to pi over 2. So it's type 2. Now let's solve this question. Now we are approaching pi over 2 here, right? Our interval is 0 to pi over 2. So we are approaching the pi over 2 from left side. So we need to look at the left limit. Limit r goes to pi over 2 from left side, 0 to r secant x dx. And from the previous lectures, we know that integral secant x dx is equal to ln secant x, absolute value of ln x, secant x plus tangent x. So this limit is equal to limit small r goes to pi over 2 from left side is equal to ln secant x plus tangent x, and this is go between 0 to small r. Boundary of this function is between 0 to r. Now, and this limit goes to r pi over 2 r goes to pi over 2 from left side ln secant r plus tangent r minus ln secant 0 plus tangent 0. Now we know that secant 0 is 1, right? Yes. And tangent 0 is 0, but ln 1 is 0. So this part cancels. So we have this limit. Now, when r goes to pi over 2, secant r goes to infinity, right? This one goes to infinity. And tangent r also goes to infinity. Sorry, secant r goes to positive infinity when r goes to pi over 2 from the left side, and tangent r also goes to infinity when r approaches pi over 2 from left side. So inside of the ln goes to positive infinity. So ln positive infinity goes to infinity. This limit goes to infinity. So this implies that 0 to pi over 2 secant x dx is divergent. So our third part is also divergent. Let's solve the part D. Part D. What was the part D? Part D is 0 to 3 1 over 9 minus x squared dx. Now, we need to find value of this integral. Now, our fx is this function. This is our fx, right? And denominator becomes 0 when x is equal to 0, right? 9 minus 9 goes to 0. So, this 1 over 9 minus x squared goes to infinity. So, fx is unbounded. At x equal to 3. So, we have type 2 improper integral. Now, we have 1 over 9 minus x squared is equal to 1 over 6, 1 over 3 plus x plus 1 over 3 minus x. We will need this in a moment. Now, we are approaching to 3, our integral between 0 and 3, and we are approaching to 3 from left side. Limit r goes to 3 from the left side, 0 to r, 1 over 9 minus x squared dx. Now, this limit is equal to. Now, to solve this integral, we can separate this one into two pieces. Limit r goes to 3 from left side, we have 0 to r, 1 over 3 plus x dx, plus 0 to r, 1 minus 3 minus x dx. So this limit is equal to limit r goes to 3 from left side. Integral of this one is ln absolute value of 3 plus x between 0 to r plus ln absolute value of 3 minus x from 0 to small r. So these limits again also equal to r goes to 3 from the right side. Ln 3 plus r, absolute value of ln 3 plus r minus ln 3 plus ln 3 minus r minus ln 3. So our limit is equal to limit r goes to 3 from left side ln 3 plus r plus ln 3 minus r minus ln 3 to ln 3, which is ln 9. Now, so we have limit, so our limit is equal to limit r goes to 3 from left side ln 3 absolute value of 3 plus r times 3 minus r times 9. Now, this part goes to 3 plus 3 goes to 6. This part goes to 6. Now, this one goes to ln 3 minus. This one goes to 6 and this one goes to 3 minus 3, right? We are at the left side of the 3. So, we are approaching to 0. We are approaching to 0, but from right side. Since we are approaching from the r left side, we are approaching to 0 from the right side. So this limit, this inside of this absolute value goes to minus infinity, so this goes to infinity. So value of this limit goes to infinity. Ln infinity is infinity. So integral 0 to 3 1 over 9 minus x squared dx is divergent. Now, our part E is minus infinity to infinity x e to the minus x squared dx. Now, we have two problems. One is minus infinity and other one is infinity. And x to the e to the minus x squared is bounded on minus interval minus infinity to infinity. So it's bounded everywhere. Now, it's type 1. But we have two problems. So, we can't attack two problems in a one time. So, we need to separate these two problems. So, we need to look at an integral something to infinity x to the e to the x squared dx, and also we need to look at the integral minus infinity to something x e to the minus x squared dx. To simplicity, let's divide two integrals at 0. So we need to look at 0 to infinity x times e to the x squared dx and infinity to 0 x times e to the x squared dx. Now, we know that if one of them is divergent, our main integral is divergent. And if two of them divergent, main one is again divergent. But if both of them convergent, main integral is equal to this integral plus this one. So, exercise for you. This integral x to the e to the x squared dx is equal to minus 1 over 2 e to the minus x squared plus c. Now, let's look at this piece. Let's consider this one. Now, we are going to minus infinity. Limit r goes to minus infinity, r to 0, x to the e to the minus x squared dx is equal to limit r goes to minus infinity minus 1 over 2 e to the minus 0 square minus plus 1 over 2 e to the minus r square. Now, this one is this one goes to 1. This one is the 1. This one is equal to 1. And this limit goes to, you can write the inside of the limit as minus 1 over 2 plus 1 over 2 times e to the r square. Now, when r goes to minus infinity, r square goes to infinity, right? E to the infinity goes to infinity. This one goes to infinity. So, this one goes to 0. So, value of this limit goes to minus 1 over 2. Now, and if you look at the other part of the limit, let's look at this part. Limit r goes to infinity 0 to r x e to the minus x square dx is equal to limit r goes to infinity minus 1 over 2 e to the minus r square plus 1 over 2 e to the minus 0 square. Now, this one again goes to 1. This is equal to 1 over 2. So, this limit is equal to limit r goes to infinity minus 1 over 2, 1 over e to the r square plus 1 over 2. Now, this one goes to 0 again. So, this limit is equal to 1 over 2. So, since both of the integrals are convergent, our main integral is convergent, and which is converges to minus 1 over 2 plus 1 over 2 is equal to addition of these two integrals. So this is equal to 0. So our integral converges to 0. The question f is minus infinity to infinity e to the minus absolute value of x dx. E to the absolute value of x minus absolute value of x is bounded on minus infinity to infinity. So it's type 1. Now, we have two problems again. So we need to divide the integral into two pieces. I choose again 0 to simplicity, 0 to infinity, e to the minus absolute value of dx. And we have another integral, minus infinity to 0, e to the minus absolute value of the x dx. I'm choosing the 0, but you don't need to choose the 0. You can choose, for example, 10,000 or like 1. Any value you can choose. Now, in my setting, we are between 0 to infinity, right? So, absolute value of x is equal to x. Again, for this integral, we are between 0 to minus infinity. So our x values are negative. So, this one is equal to minus x. So, this integral becomes 0 to infinity e to the minus x dx. And this integral becomes 0 to infinity e to the x dx. Now we need to solve these integrals. Minus infinity to 0. Now we have, let's look at this one. Limit r goes to minus infinity. Minus infinity to 0, r to 0 e to the x dx. And we know that integral of e to the x is equal to e to the x. So we have limit r goes to infinity, e to the x, boundaries are r to 0. So it's equal to limit r goes to infinity, e to the 0 minus e to the r. So r goes to minus infinity, sorry. Right now we are looking at the minus infinity. So e to the 0 is equal to 1. And when r goes to minus infinity, e to the r goes to 0. So this limit goes to e. Sorry, not to e. This limit goes to 1. E to the 0 is 1. Now, if you look at the other piece, limit r goes to infinity, 0 to r, e to the minus x dx. Integral e to the minus x dx is equal to minus e to the minus x plus c. So this limit is equal to limit r goes to infinity, minus e to the r, minus minus become plus, e to the 0. Now, e to the minus r, sorry. When r goes to infinity, e to the minus r goes to, this one goes to 0, and this one is equal to 1, so this limit is equal to 1. So we have, so both of them convergent, so our main integral is equal to minus infinity to infinity e to the minus absolute value of x is absolute value of x dx is equal to 1 plus r, which is 2. So our integral converges to 2. Now we pass to second question. Second question is determine whether the given integral converges or diverges. For this question, we don't need to find the value the integral converges. We just need to determine whether the integral converges or diverges. So we will use the tests. I want to remind you the test. Now, we have the p-test, right? If we have the integral a to infinity x to the minus p dx, this integral is convergence if p is greater than 1. And this integral is divergence if p is less than or equal to 1. And the other case is a to p, 0 to p, x to the minus p dx. Now, for this one, this integral is convergent if p is less than 1 and divergent if p is greater than or equal to 1. So, if the integral is type 1, p must be greater than 1. And if the integral is type 2, p must be less than 1. At p is equal to 1, it's always divergent. Now, our second test is comparison test. For this comparison test, we have two functions, fx and gx, both of them greater than equal to 0. This is the most important case. And f and g are continuous on a to b. A to b. So, now, a to b gx, if the big one, which is a to b gx dx, convergent, small one will be convergent. Since it's between 0 and the gx, it must be convergent. Now, if the small one is divergent, this say that big one must be also divergent, because big one, integral of big one will be greater than integral of smaller one. Our third test is limit comparison test. For this test, also we also need that fx and gx must be positive, and they must be continuous. And we are looking at the limit at the improper point. Limit x goes to b from left side, fx divided by gx is equal to, say, L. And if this L is a positive number less than infinity and which is not equal to 0, this implies that both of them convergent or both of them divergent. They have the same value, not the same value, same convergence type. Let's say not the same. Okay. If n is equal to 0, we can say that numerator bigger than denominator. So fx really greater than gx. And if this L is infinity, we can say that denominator bigger than numerator. Gx is greater than fx. If you see that for both of the tests, fx and gx must be greater than equal to 0. If you say what will happen if fx or gx is negative, we can look at the absolutely convergence. An improper integral a to b fx dx is converges absolutely if a to b absolute value of fx dx is convergent. Okay, but you need to remember that these are just one-sided. You cannot say that if a to b fx dx is convergent, this implies that a to b absolute value of fx dx convergent. You cannot say that one. This is not true. A to b fx dx convergent does not imply that a to b absolute value of fx dx convergent. This is important. Let's solve the first question. Part A. Part A is integral 154 to infinity x over x to the 2020 plus 1 dx. I want to solve this question with two ways. First way, you can solve this question with the comparison test. Now, first way, we can solve this question in the comparison test. Now, x is greater than 154, right? So, this value is always greater than 0. Now, we need to bound this function with some other function. Now, we know that x to the 2000, we have x to the 2000 plus 1, right? X to the 2000 plus 1, x to the 2020 plus 1 is greater than x to the 2020, right? So we can say that with this inequality, we can say that x over x to the 2020 plus 1 less than x over x to the 2020. So this is equal to 1 over x to the 2090. Now we know that this function less than this one. And we can solve this one easily from the p-test. Now we have the integral 154 to infinity 1 over x to the 2019 dx. Now this is the form of p-test, right? We have a to infinity x to the minus p dx. In our case, p is equal to 2019, and which is obviously greater than 1, right? So this integral is convergent. We have a to the infinity x to the minus p dx, and RP is greater than 1, so it's convergence. It's convergent by p-test. Now, we know that bigger one is convergent, so small one becomes convergent, right? This big one is convergent, then small one must be convergent. So 154 to infinity x to the 2020 plus 1 dx is convergent by comparison test. I want to solve this question also with the second way. Second way will be limit comparison test. Now, let's close this side and not look at this one and try to solve this question again. Now we have x integral 154 to infinity x over x to the 2020 plus 1 dx. Now, degree of the numerator is 1 and degree of the denominator is 2020. So difference between these two degrees is 2019, right? So we can compare this function with the our fx is x over x to the 2020 plus 1, and we can choose gx as 1 over x to the difference of degrees, and the difference of degrees is 2019, right? And let's look at the limit. And also both of them greater than 0, greater than or equal to 0, and both of them have problem only on infinity, only at infinity. So now we can look at the limit x goes to infinity, x over x to the 2020 plus 1 over gx. So this is equal to limit x goes to infinity, x to the 2020 over x to the 2020 plus 1. Now, we can cancel x to the 2020s from the numerator and the denominator. Then we will have x goes to infinity 1 over 1 plus 1 over x to the 2020. So this part goes to 1 over infinity goes to 0, right? So 1 over 1 goes to 1. Now, our limit goes to 1, right? And 1 is between 0 and infinity, and it's not equal to 0. So we can say that both of them convergent or both of them divergent. Now, again we have that, if we take this part, we know that this one is convergent by p-test. Previously we showed that. So we can say that they have the same, right? They have the same convergence. Plus 1 dx and 154 infinity 1 over x to the 2019 dx have the same convergence. So this is convergent by p-test. So this is convergent by limit comparison test. So you can solve this one like this in two ways. You can also find like a lot of different ways. These ways are not unique. You can choose x to the 1 over x to the 2017 or something, or x to 2021. It's your preference. Of course, one of them will not work. For the part B, again, let's take this one here. Now, again we have 4 to infinity, fifth root of x cubed plus 2x over cube root of 2x to the 5 minus 4x plus 1 dx. Now, biggest degree in the denominator is 3 over 5, right? And the biggest degree in the denominator is 5 over 3. And the difference between them, 5 over 3 minus 3 over 5, is 25 minus 9 over, over 15, which is equal to 16 over 15. Yes, 16 over 15. Over 15. Now we have difference between these two functions is this one. So we can divide, we can look at this one. Now let's choose fx's, our fx. Fx is this one. Let's compare our fx and gx, which is equal to 1 over x to the difference 16 over 15. Both of them greater than 0, since x is greater than 4. Now, we have fx and gx, both of them greater than 0. Now, let's look at the limits again. We have limit x goes to infinity, fx over gx. This is exercise for you. If you solve this, this one is equal to 1 over cube root of 2, which is greater than 0 and less than infinity. These are finite numbers. So, both of them convergent or both of them divergent. Integral 4 to infinity fx dx and 4 to infinity gx dx they have the same convergence. Now, if you look at our gx, in this case our p is 16 over 15, right? Again we are at the a to infinity x to the minus p dx, and p is equal to 16 over 15 greater than 1, so it's convergent by p-test. Now, since this one is convergent, this one is also convergent by limit comparison test. Now, part B is over. Let's look at the part C. Part C is 1 to infinity cos x to the 4 over 154 plus x to the 4 dx. Now, again we know that cos to the 4x is between 0 and 1, right? Cosinus x is between 0 and 1, so cosinus x to the 4 is between 0 and 1. So, cosinus x to the 4 over 154 plus x to the 4 is between 0 and 154 plus x to the 4, right? So we know that this one is also less than 1 over x to the 4, right? We add 154 to the denominator, so this is less than this one. Now, again we have 1 to infinity 1 over x to the 4 dx. Again, p is equal to 4, right? And we are at the 1 to infinity, p is greater than 1. So this implies that it is convergent by p-test. So big one is convergent, so small one must be convergent. So 1 over 1 to infinity cosinus x to the 4 over 154 plus x to the 4 dx is convergent by comparison test. Comparison test. Part D is minus 1 to 1 e to the x over x plus 1 dx. In this question, denominator is equal to 0 at x equal to minus 1, right? So, e to the x over x plus 1 is unbounded at x equal to minus 1. E to the x plus 1 is unbounded at x equal to minus 1. Unbounded when x goes to minus 1. So our problem is here. So we can do the limit comparison test here. Now, we have e to the x over x plus 1, right? Our problem is 1 over x plus 1. E to the x does not have a problem. So we can look at e to the x over x plus 1 and 1 over x plus 1. This is our gx and this is our fx. Both of them greater than 0. And both of them have problem at x equal to minus 1. When you are doing the limit comparison test, they must have the problem at the same point. Limit x goes to minus 1. We are approaching the minus 1 from the right side. X goes to 1 from the right side. E to the x over x plus 1 over 1 over x plus 1. Now, both of them cancels each other. So this limit is equal to limit x goes to minus 1 from right side. E to the x is equal to e to the x is equal to 1 over, which is a number greater than 0 and less than infinity. So they have both have the same convergence or divergence. So now we need to find what is whether this one convergent or divergent. Now, this integral is equal to, we have a problem here, right? So we can look at this limit. Limit x goes to minus 1 from right side, 1 integral minus r goes to minus 1 from right side, integral r to 1 over x plus 1 dx, which is equal to limit r goes to minus 1 from right side, ln x plus 1, and boundaries are r and 1. So this limit is equal to limit r goes to minus 1 from right side, ln 2 minus ln absolute value of ln r plus 1. Now when this goes to minus 1 from right side, this one goes to 0, but goes to 0 from right side. So when ln inside of the ln goes to 0, this one goes to minus infinity, right? So we have ln 2 plus infinity. So this limit does not exist. This limit goes to infinity. So integral minus 1 to 1 over x plus 1 dx is divergence. So this implies that we find that from limit comparison test they have the same type. So this implies that minus 1 to 1 e to the x over x plus 1 dx is divergent by limit comparison test. And the part E is integral 0 to 1 x to the minus 1 over 2 cosinus x dx. Now we are at between 0 and 1, right? So cosinus x is always greater than 0. Cosinus x is always greater than 0 and less than 1 since x is on the open interval 0 to 1. Now we have cosinus x to the square root of x. Now if you compare this function with our fx is x to the minus 1 over 2 cos x, right? And we can take gx as x to the minus 1 over 2, both of them greater than or equal to 0. Now we can use the limit comparison test again. Also we have our problem is at 0, right? For this one and for this one also. Limit x goes to 0 from right side, x to the minus 1 over t cos x over x to the minus 1 over 2. Now these are cancels each other. So we have limit x goes to 0 from right side cosinus x, which is equal to 1. So this is a finite number greater than 0 and less than infinity. So this gives us this limit. We need to find whether this integral is convergent or divergent. 0 to 1 x to the minus 1 over 2 dx. Now we are at this case, right? We have 0 to a x to the minus p dx, and our p is equal to 1 over 2 less than 1, so it is convergent. It is convergent by p-test. So our main integral 0 to 1 x to the minus 1 over 2 cos x dx is convergent by limit comparison tests. And the question F is 0 to 1 square root of x ln x dx. Now, between 0 and 1, ln x is less than or equal to 0, right? When x is between 0 and 1. So, square root of x ln x is less than 0. So, we cannot use comparison test or limit comparison test. So, let us look at the absolute value of fx, which is integral of absolute value of fx. 0 to 1 absolute value of square root of x ln x dx, which is equal to, since square root of x greater than 0, integral 0 to 1 square root of x absolute value of ln x dx. Now, we need to compare this one with something. We need to compare this function with another function. Let's try to... What can we try it? For example, let's try 1 over x. What will happen? If we try 1 over x, let's choose gx is equal to 1 over x, right? If we try gx is equal to 1 over x, what we will have, this is also greater than 0, and this one is also greater than 0, and both of them have the problem at x equal to 0. So let's look at the limits. Limit x goes to 0 from right side. Square root of x ln absolute value of x over 1 over x. So we have limit x goes to 0 from right side. Absolute value of ln x over 1 over x to the 3 over 2. Now, this one goes to infinity, right? And this one goes to infinity. This one is also goes to infinity. So we have infinity over infinity. So this is equal to limits. Let's write this one as absolute value of ln x is minus ln x, since ln x is always negative near 0, 1 over x to the 3 over 2. Now, this is equal to infinity over infinity, so we can use the L'Hopital's rule. So we have limit x goes to 0 from right side. Derivative of minus ln x is equal to minus 1 over x, and derivative of minus 3 over 2 is minus 3 over 2 times x to the minus 1 over 3, x to the minus 5 over 2. So this limit is equal to limit x goes to 0 from right side. We have x to the 5 over 2, x to the 3 over 2 times 2 over 3. Now, this limit goes to 0, right? So this implies that gx is really greater than fx near 0. Now, we have that this one 0 to 1 over x dx is p is equal to 1, right? P is equal to 1. At p is equal to 1, this integral is always divergent. Divergent by p-test. But if this one divergent, this doesn't say anything about the small test, so test fails. We need to choose a new function. And not the 1 over x, we need to choose something else. Now, again, our fx was square root of x. Our fx is this one, square root of x, absolute value of ln x, and which is always greater than 0. Let us choose gx as 1 over square root of x. Right? Yes, 1 over square root of x. And it's also greater than 0, and its problem at 0. Now let's look at the limits. Let's use this one. Limit x goes to 0 from right side ln absolute value of ln x square root of x over 1 over square root of x. Now, this limit is equal to, for trying the second thing, I'm not I want to say that I did a mistake before. If L is equal to 0, fx is less than gx, and if L is infinity, gx is less than fx. Now, if you pass to here again, right now we are trying to function 1 over square root of x, and we have these limits. So this one gives us limit x goes to 0 from right side minus ln x over 1 over x. We have 1 over square root of x here, and 1 over square root of x, we have 1 over x. And this one goes to infinity, and this one goes to minus infinity. So we have minus infinity over infinity, so we can use the L'Hopital. So this limit is equal to limit x goes to 0 from right side minus 1 over x over minus 1 over x squared. So this is equal to limit x goes to 0 from right side x, so this limit goes to 0. So this says that again numerator, which is gx, is greater than fx. Now we have this integral, right? 0 to 1 1 over square root of x dx. Now again, if we remember the p test, we are here 0 to a x to the minus p dx, and our p is 1 over 2, which is less than 1. So this integral is convergent by p test. So if this integral is convergent, this gives us, this bigger one is convergent, this implies that small one is also convergent, right? So 0 to 1 square root of x, absolute value of ln x dx is convergent by limit comparison test. So this fx was absolute value of our function, our main function. So this implies that 0 to 1 square root of x ln x dx is absolutely convergent. Okay. I did a mistake and I forget to push the button. So I will show this one again. Now, for the last part, we have the integral 5 to 7 1 over x squared plus 3 times cube root of 7 minus x and times cube root of x minus 5. Now, we have two problems, 5 and 7, right? When x goes to 7, this part goes to 0, and our fx goes to infinity. And when x goes to 7, when x goes to 5, this part goes to infinity, 0, so all fx goes to infinity. Now, so we need to separate this integral into two pieces. One piece becomes 5 to 6 fx dx, and other piece will be 6 to 7 fx dx. Let's say this is A and this is B. Let's try to solve to A. A is the integral 5 to 6 fx dx. Now, between 5 and 6, fx is greater than 0, and let's take the gx as 1 over cube root of x minus 5, which is also again greater than 0. Now, when x goes to 5, fx over gx goes to 1 over 26 times cube root of t. You can show this by yourself. So, since this is a non-zero bounded value, this implies that integral 5 to 6 fx dx and 5 to 6 1 over cube root of x minus 5 dx have the same convergence. Both of them convergent or both of them divergent. Now, let's look at the 5 to 6 1 over cube root of x minus 5. For this question, I want to use the p-test. So I can change the variables. Let's say x minus 5 is equal to u. Then dx becomes du. So this integral becomes 0 to 1, 1 over u to the 1 over 3 dx. So for this one, we will use this part again. Rp is, what was Rp? Rp is 1 over 3. So Rp is less than 1, so this integral is convergent. So this integral convergent means that this one is also convergent. So this one is also convergent means that our integral A is also converged by limit comparison test, since limit value was finite number, finite non-zero number. B is also convergent. I'm giving you as an exercise. Since both of the pieces are convergent, this integral goes to A plus B, so this means that it's convergent. We come to the end of this class. See you next week. Bye.